So it'll take us 2 days to get all the way through this. We'll actually kind of get through C and be starting D, hopefully, by the end of today. We'll combine A and B, we'll do those together. So we're talking about linear inequalities now. So yesterday, when we did the non-linear, like the circle and the line, now we're just looking at linear inequalities, because that's going to help us solve these linear programming problems. Linear programming problems are lengthy problems to do, so we won't get through all of it today. You might remember doing it. I don't know if you did it in Algebra 1 or Algebra 2, because they changed the curriculum on when you learned it. But it talks about like constraints. I don't know if that word sounds familiar to you at all. And maximizing and minimizing. Okay, so first of all, let's just talk about, this is actually A and B. So objective A is like doing one inequality, B is doing the system. So we talked about this yesterday, but the system, the solution is the overlapping shaded region. Okay, so both of these graphs are linear. I want to talk about doing this line, graphing this line. I've started grading the quizzes. I've only made it through the first page, but some of you still struggle with graphing lines. So I want to make sure I step through this. Okay, so when I graph the lines, I want to put it in slope-intercept form. Okay, so I want y by itself. I will add x first. So 5y is less than x plus 5. Here. Let me write that out. So add x, and then I divide by 5. So both terms have to be divided by 5. 5 is positive, so I don't have to flip the direction of my inequality. X over 5 is 1x over 5. So that's 1/5 x. So I want to make sure I keep my slope as a fraction. And then 5 over 5 is 1. Okay, so 1 is your y-intercept, so that is where you'll start. And 1/5 is your slope. Okay, so I'll go ahead and graph this. So my slope is 1 over 5. It's rise over run. Okay, so I'm going to go up 1 and right 5. Or I could go down 1 and left 5. Okay. Will this line be solid or dashed? Dashed. Good. Now let's think about the shading. Will I shade on the side of the line that's above or below the y-intercept? Yeah, it's less than, so I'm going to shade below. So down here, I am going to wait just a second to do my shading, because I'll just shade the final overlapping part. Okay. Take a second and do this one. Okay. So get y by itself on your second inequality. So Alyssa, what would I do first? Subtract the x. Good. So Alyssa, what does that right side look like now? Good. Negative x plus 1. Good. Okay. Kyle, what would I do next?
Start 2 on both sides.
Okay. So Kyle, what does the right side look like now?
-1/2 x.
Very good. -1/2 x plus 1/2. Okay, good. Okay. Lauren, where would I start? Okay, good. And then Lauren, my slope is -1/2, so how would I move? Good, down 1, right 2. Adam, will my line be solid or dashed? Okay. Adam, will I shade above or below, the side that's above or below my y-intercept? Above, yes. Yeah. So greater than, you shade on the side that's above, so that's, here's the y-intercept. Okay? So I'm just going to shade in now where they overlap. So they'll overlap in this region here. Okay? So that's the solution.
What would the question be for this on the test?
I'll show you just a second. Okay, so there's the solution. So these would be the directions, okay? I put it here because we'll do the test point. We'll do the test point now, okay? Okay, so my solution is this region. And now if I want to pick a test point, I could pick any point in that region. So what's one I could choose? Let's pick one on an axis because then at least one variable is 0 and that's easy to plug in. I heard 5, 0. Okay. All right. So let's plug that in. So I'm just going to do that work here. So plug that into each inequality. Okay. That's -5 plus 0. That's -5. Is -5 less than 5? Yes. Okay. And now 5 plus 2 times 0, which is 0. 5 plus 0 is 5. Is 5 greater than or equal to 1? Yes. Okay. If you want to write this down and look at some graphic calculator stuff, there's a way that you could change the calculator so it will shade for you. I don't necessarily think it's necessary for you to do that on your calculator. If anything, maybe it would help you check that you shaded correctly, but you still have to know if it's above or below you still have to tell the calculator where to shade. So I mean, it's kind of interesting. It's kind of cool that it will do that for you, but you still have to know everything. It's really, I don't know. It really just gives you a pretty picture more than actually helping you. So anyway, if you're curious, you could look. Okay. So now we're going to talk about some applications here. And we're going to start building just what we need to do a linear programming problem. Okay, so the first thing I want to know is these two inequalities. Your x is greater than or equal to 0 and y is greater than or equal to 0. So that tells me x needs to be positive and y needs to be positive. So that's why my axes look like this, because I'm only interested in what's in the first quadrant now, because that's where x and y are both positive. Remember that x greater than or equal to 0, x equals is a vertical line. So this is my y-axis. I know that seems weird because it's x, but that's what gives us the equations of vertical lines. So that's my y-axis. This is my x-axis. All right, I'm going to go ahead and draw my arrows showing that I would shade this way because it's positive and this way because it's positive. That's going to come in, those are going to be sort of like our hidden inequalities, our hidden constraints when we're doing the linear programming. Because like if we're trying to find like the number of cars and buses, then we know we're not going to use negatives. You're not going to have a negative car or a negative bus. So you would use these two inequalities, but it wouldn't necessarily tell you, like, you're not going to have negative cars, you're not going to have negative buses. That's something that we should know. Okay. Right now, I don't have a word problem. Those are just given to me. Okay. All right. So now, let's look at this one. And we could put it in slope-intercept form, okay? Or you can find your x and y intercepts. Sometimes it's easier to do it that way. Let's go ahead and put it in slope-intercept form, though, because that's what we've been doing, and then I'll show you the intercepts. So let's subtract 8x. And divide by 5. So negative 8/5 x plus 8. So I'd wait to set your scale until you have it changed to slope-intercept form, just because sometimes you could be dealing with big numbers. 8's fine though, but you could have like 25 as a y-intercept, so you want to make sure you could get to 25. So I'd wait to set your scale till after that point. I'm fine to count by ones just with an 8. So if I do that, 17, and this would be 17. Okay, so I'm going to start at positive 8, and then I'll go down 8 and right 5. Why is it 17? Oh, like my scale is 17. Like if I count 1, 2, 3, 4, 5, I counted by ones. Oh. So that the top is 17 if I count by ones. A lot of times, you know, you can put your scale right here, but that ends up, I feel like, getting in the way more often than just writing it up there. That's why I always put the scale at the end. Okay, so I can graph that. Will it be a solid or dashed line? Solid. And will I shade above or below the line intercept? Below. Less, below, above, greater, above. Okay, so below. I'm down here. Okay. I also wanted to show you that you could graph that line using your x and y intercepts. So remember that cover-up method. If you want your x-intercept, you cover up y. So 40 divided by 8, so 5, 0 is a point, and then 0, 8 is a point. Okay, so you could graph it like that. You just have to be careful with your shading, because if this were a negative y, there were a negative right here, then you would divide and your inequality would flip. So that's why we usually graph inequalities in slope-intercept form, because then you can look at the inequality sign to see where you shade. So just be careful. Okay, so I overlap. I need to be right of the y-axis, above the x-axis, and then below this red line. So I have just this triangle right here. So when we get to linear programming problems, we're going to have a bounded region like this. It'll either have 3 or 4, we say, corner points. So like the vertices. So this is a triangle, so there are 3. Okay. What is inside here, the overlapping region, this is called our feasible region. So that's our solution, because anything inside there is feasible. It fits all of those inequalities. And I should say region. Feasible region is what it's called. Okay. It's your solution. All right. Let's list those corner points, because once I get to, like I said, solving a linear programming problem, I'm going to have to identify where the corner points are of my feasible region. So I have 0, 0, 5, 0, and 0, 8. If it wanted you to list these, it would tell you to list the corner points. Okay? So, what we are trying to do is kind of figure out the parts of a linear programming problem. So when we do a linear programming problem, it's a word problem. And we will have to come up with our constraints based on the information it gives us. So we'll have to write these ourselves. We'll have to graph them. We will have to find their corner points. And then we plug these into an equation that we will find to maximize or minimize, like to find a maximum or minimum. Okay? So just hang with me now. You might not quite understand why we're finding this, but you will once we do the whole thing. Yes? Test point? Yes. However, if one of these were dashed, right? If one of these were dashed, then it wouldn't be true because it's on the line. It wouldn't be equal to it. So you can use them to check now, but they will check whether they're equal, not necessarily satisfying the inequality. Okay. this is our y-axis. Okay. And so I want to, it's greater than or equal to, so I'm going to be right the y-axis. Okay. So then this first line, get y by itself, so just divide by 4. So that's 3/4 x plus 3. My third line is already in slope-intercept form. My y-intercept is just 1. So my scale, I can just count by ones. That would go to 17 there, and 17 again. If I graph my first inequality, I'm going to go up 3 to 3. And then from there, I want to go up 3 and right 4. Will this be a solid or dashed line? Dashed. Okay, good. Okay. I'll grab, and let's see, it's less than, so that above or below? Below. So I'm down here. Now my third inequality, my y-intercept is 1 and my slope is 1, so up 1, right 1. Will this line be solid or dashed? Solid. So, I've got to do my shading. This line will I be above or below the y-intercept here? Above. So my overlapping part is just in this little section right in here. Okay, and the y-axis. Don't forget about that. So okay, depending on how accurate you've drawn your line will be whether or not you can tell where this point is. Okay, so my quarter points, I have 3 again. So I have 0, 1, and 0, 3. And then I have this one. So I think I drew my lines pretty accurate, but I need to make sure that that's right. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 8, 9 is right now my guess. Okay, I'm guessing that that's the third one. So if you guess, you can either plug them back in to the equation. So you want to look to see where they intersect. So when you're looking for a point where they intersect, we're not looking now at the inequality, we're looking at the equation. So you would look at these as equations and plug them in there and make sure that they're equal. Another way, because let's say your guess is really off, another way you can be sure is to solve the system. So check 8, 9. So I'm checking 8, 9. So I'm going to look at those two lines as equations. And I am going to solve this by substitution. So I'm going to plug this in here. Okay, so 4x plus 4. Subtract 3x, subtract 4, so x equals 8. If I plug that back in to y equals x plus 1, y is 9. So that is the third corner point. It's important to know that needs to be accurate because that could be the point that gives you a maximum or minimum. Since I'm looking where they intersect, that's why I'm looking at the equation. Okay, so I'm solving the system of equations to see where they intersect. You can plug them in, but that's if you have a good guess. Okay, so it just kind of depends on how accurate your line is. I need to see that you've checked it somehow, either like this or by plugging it in. And when you plug it in, you need to plug it into the equation. They need to be equal, okay, not just the inequality.
So when do you make it equal and when do you keep it at inequality?
So when you want to know where two lines intersected, when you want to know that specific point, you're looking at the solution to the equation. There's only one point that that's true for. When you're solving just an inequality, when you're getting a feasible region, you're looking at the inequality, because any of these points will make the inequalities true, but only this point makes the equations true. Okay? Okay, so we're going to start this next part. So our goal for solving a linear programming problem is to maximize or minimize an objective function. So we'll be given a word problem, and just like any word problem, the first thing we'll do is identify what x and y represent. And then we'll be able to write an objective function. So it'll give us information where we can write an objective function. This is what an objective function looks like. It seems kind of weird seeing that f of x comma y, but all that means is that you plug your x values in for x, your y values in for y. Okay, so we'll identify variables, write the objective function, and then we will come up with our constraints. So our constraints will be the limitations that it'll give us. It'll say things like, well, you only have this amount of space. So you have to take that into consideration. These are what you graph. You graph the inequalities. You do not graph your objective function, you graph your inequalities. You will use your objective function once you have your corner points. So it's a fact that your objective function will be maximized or minimized at one of the corner points, at one of the vertices. Okay? So that's why it's important that I find those corner points. So let's graph. This is my y-axis. This is my x-axis. So I know that I'm right. My y-axis, I'll come back up just a minute, and I'm above my x-axis. Okay? I want to wait to set my scale. All right, let me subtract 2x. So that's negative 2x plus 7. And then this one, I have to subtract x and then divide by 2. So negative 1/2 x plus 5x. Okay. So I think I could count by ones. This time, 1, 2, 3, 4, 5, 6, 7, 8, 9, 16. Okay. I'm going to start with the first inequality, so the one I have in red. So I'm going to start at 7. And my slope is negative 2, so down 2 and right 1. Okay, this will be a solid line. And it's less than or equal to, so I'm shading below. The second one, I'm starting at 5/2, so 2.5. And my slope is negative 1/2, so down 1, right 2. And this is also a solid line. And I'm shading below. Okay. So I overlap in here, and now I have a 4-sided feasible region. Like here's a point, point, point. So I'm here. So I have 4 corner points this side. If they're on an axis, you can tell by looking at it. You don't have to check. So 0, 0, 0, 5/2. I need to find the x-intercept of the red line because that's my corner point here. Remember, if you want the x-intercept, you could cover up y. So 2x equals 7. So that's 7/2 or 3.5. If you can use the decimal if you don't have to round. So this is 7/2, 0. And then it looks like I have 3, 1. Okay, that is the one I need to check. So 2x plus y equals 7, because I'm looking at the equations now. X plus 2y equals 5. Substitution or elimination. If I do elimination, I'll multiply the bottom one by negative 2. Okay. If I add down, I get negative 3y equals negative 3. Y equals 1. Plug that back in. 2x plus 1 equals 7. So x equals 3. Subtract 1 and 6, divide by 2. So 3, 1. Right. Okay. Now, I plug that in, all 4 corner points, into my objective function. See which one gives me the biggest number, and that is my maximum. So plug into f of x, y equals 8x plus 5y. So I would take each one. So 0, 0, 0, 5/2, 7/2, 0, and 3, 1. Like this. Substitute them in for x and y. That's 29. And whatever one is the biggest. This one's 0, right? 8 times 0. This is 25 halves, so 12.5. It might be this one. And then it's 20. No, it's not, because this is 26. So 8.5. So this is my maximum. Okay. All right, so we'll do the whole entire thing then on Monday.